continuing the series. We're coming to the last of these. Next week, as most of you know, we're going to be looking at the Green New Deal and beyond, uh, done by Stan Cox, who's the lead scientist at the Land Institute, which is in Salina, Kansas. So the way we have come to this has been going on now for, I don't know, several years. This is the first time we've ever been on Zoom. It's coordinated by the ECO team of the First Presbyterian Church. Um, Being a Earth Care congregation, uh, we work to be aware and have concern for Earth Care in our worship, our education for the plant, and also in terms of our outreach. So we also work through Lettuce. Lettuce is Lawrence Ecology Teams United for Sustainability, and this is really an interfaith team made up of, and I want to list them in just a moment, but this is our advocacy group. Although we do advocacy with each of our green teams in this, we unite to do advocacy and try to be supportive where we can and raise comments with both city and county and also in the state legislature. Most recently, we've been dealing with the state legislature and their issue about choice in terms of energy, and been an interesting experience there. But Lettuce, Lawrence Ecology Teams United Sustainability is composed of the First Presbyterian Church and Lawrence Jewish Community Congregation, Unitarian Universalist Congregation, Plymouth Congregational, the Oriented Friends, the Quakers, St. John the Evangelist Catholic Church, and Islamic Center of Lawrence. All of us meet regularly. That is, the representatives of that and a steering team, and we go from there. Uh, Kind of a general procedures is we'll keep you on mute. If you have some comments and you'd like to join us and chat, and for anybody that's new, chat's there down at the bottom, and you've already can click on that and you can see somebody. Joe and Rick Randolph, Kansas City, have come up, and I want to say something a little bit. I learned through them about the wonderful program that Rotary has as far as Earth Care, etc. So if you have anything that you want to ask or make a comment, please go on chat. Mark has agreed to check that out. If you have any questions, why ask them, and you have any comments too, he'll be looking at that. Well, let me, I think that's it. Also, there's recording. Okay. I want to say, Mark has got this wonderful bio, and I'm going to be skipping over too much, but I want to say a little bit about him, so kind of introduce you to him. He's was raised in Cary, North Carolina, and attended North Carolina State University in his undergraduate years, and was very interested, of course, in chemistry. And he, in his junior year, he worked for the DuPont company in Delaware in their works plant. And he then went, after that, he realized he was in the right direction, and he graduated magna cum laude and went to work for DuPont. And they handed him a first assignment, and that was to develop new refrigerant mixtures to replace chlorofluorocarbons, CFCs, which were linked to the depletion of the Earth's ozone layer. Some of you are probably familiar with that. And his discoveries led to 30 US patents, and he has many more than that now. But these are in the development of 3 commercial refrigerants that are sold worldwide for use in commercial and air conditioning systems, and has been important in restraining the release of gases, the noxious ones. After completing his PhD, he developed microporous carbons for safely storing hydrogen onboard fuel cell powered vehicles for DuPont, General Motors, and Toyota. Um, he was awarded the DuPont Bolton Carruthers Award. This is one of several, but I want to mention this in 2005, and was a Hero of Chemistry Award. In 2006, the University of Delaware gave him a presidential citation for his development of hydrofluorocarbon refrigerant mixtures. It was important for him to do that. He's, of course, with the American Institute of Chemical Engineers, and he is loves teaching. I've learned that he has many graduate and postdocs as well as undergraduate, and he loves to do that. He is now a distinguished foundation professor in the Department of Chemical and Petroleum Engineering at the University of Kansas, which is a very distinguished position. And he is a member of the ECO team at First Presbyterian. So, Mark, again, thank you for giving us time, and I'm just going to turn it over to you from here. Thank you much.
Well, Thad, thank you very much for that very kind introduction. And I'm going to share my screen. So
yeah,
let's see. Can everybody see that?
Yeah.
All right. And you can see the little marker on the screen.
Yeah, I'm seeing it.
All right, good. Well, again, thank you very much for this opportunity to talk with you. And I thought I would start out by just giving you a little bit of background. Let me see if I can change my slides. Okay, there. Everything changed okay?
Yep.
Yeah, so I'll start out a little bit with just a little bit of background about myself, and then I'll go into an interesting story. I always enjoy telling stories, especially to my students. And this is about solving a global crisis that we were having, and it was related to our ozone layer around our Earth. And then I'll talk a little bit about some grand challenges that we face today, and then offer some concluding remarks. And certainly, if you have questions, I'll be happy to answer them. So, as Thad mentioned, I worked for the DuPont company, and this is a picture of the site that I worked at in Wilmington, Delaware. It was very much like a college campus. It was composed of about 50 buildings. This is my building here, and my office used to be right about there. And I worked there for 29 years, so pretty significant part of my life. I went to work for them when I was 20, and I retired when I was 50. And while there, I worked on environmentally friendly refrigerants, but also on many other projects. Another one related to manufacturing of titanium dioxide, which is the largest white pigment made in the world. But I had the opportunity to retire, and so I wanted to show you a few products that DuPont makes. Some of these may be familiar to you. Nomex is used in firefighting equipment. It's a fire retardant fiber. Kevlar is used in making bulletproof vests. I'm sure everybody's familiar with Teflon and used in non-stick coatings. Oftentimes you'll see Tyvek home wrap on new construction. Nylon was invented at DuPont. Some of the newer fibers like Lycra and Sorona, and Kapton is used in just about every electronic device known. So the company has a very rich history of invention. And I think that's kind of what instilled in me this idea of being able to invent new things. And then coming to the University of Kansas in order to be able to help students learn how to do that as well. So in 2016, I retired. And I joined the University of Kansas. When I was in Delaware, I also taught part-time at the University of Delaware. So now I've got about 10 years of teaching experience. Our work here at the University of Kansas is focused on developing sustainable products and processes. And we do that with a lot of different types of advanced materials. And we'll talk about a few of those this morning. I like to show a lot of pictures of my students. These young people are really the reason that I'm here. We have a pretty diverse group of both men and women. They come from many different countries. This young lady, Nicole, is from Costa Rica. Kaylin is from New Mexico. Abby is from Southwest Kansas. Raj is from India. Kareem is from Pakistan. So they come from all different walks of life and all different places, but yet it's been just a real pleasure to have them in our group working on these projects together. So the topic I want to talk about this morning is something that all of you are very familiar with, and that is refrigeration and air conditioning. And it's become such a common aspect of our lives that we almost don't even think about how important it really is. But, you know, in order to have fresh food in a supermarket and have that food delivered, you have to have refrigeration. In order to live in many places around the country and the world, you have to have air conditioning. You wouldn't have the populations that you have in the southwest part of the United States today if there was not air conditioning. This has been in the news a lot lately, right? You have to have refrigeration and in sometimes very, very cold temperatures in order to keep things like medicines and vaccines stable so that they can be used. It's a part of our entertainment, and it's certainly a part of large-scale manufacturing. But, you know, the question is, where did it all begin? It wasn't that long ago, maybe about 150 years ago, where refrigeration in the aspects that we know it today did not exist. And so if you wanted something refrigerated, this is sort of what had to take place. They had to cut blocks of ice out of a lake in the middle of the wintertime, and then store those blocks of ice in buildings that were either insulated very well or in caves. And then those blocks of ice would be delivered to your home. And you had in your house something that was called an ice box. And maybe some of you might even remember your grandparents having something like this, or great grandparents. And there's the block of ice. And as it melts, it cools and keeps the products cool. Not very efficient, and certainly not really scalable to a lot of homes. And so people started to investigate artificial refrigeration. And I just show a couple examples. This is in the 1850s and 1860s. And I found it interesting that James Harrison, he was actually a journalist, was experimenting with vapor compression. And this was sort of what his refrigerator that he was trying to design looked like. And he was using fluids like ethers and alcohols and ammonia. And we'll talk a little bit more about that in a minute. The first engineer came along a few years later. He was a French engineer, Fernand Carré, and he was developing an absorption type of refrigerator where they were using ammonia and water. And then Carl von Linde, a German engineer in the 1860s, was experimenting with ammonia, sulfur dioxide, methyl chloride, and this is a picture of his refrigerator. You can see they're massive in size, not something you could easily put inside your kitchen, but these were sort of the first prototype refrigerators that were being designed. So let's fast forward from the 1860s to 1927. So 1927 were the first refrigerators made by General Electric. And these refrigerators were called monitor top refrigerators, and sort of because of this design. And they came in all these beautiful colors. So you could pick your choice of color for your home. And they were the first refrigerator that you could actually plug in to an electrical outlet in your house and keep the product inside cool. So if you think about where we had come from 1850 and using a block of ice cut out of a lake to not more than about 60, 70 years later, now you've got your first electric refrigerator. But there was one problem with these refrigerators, and that was that the refrigerant that was inside the refrigerator that helps keep it cold, they were using pretty toxic, corrosive, and flammable materials. So you probably didn't expect to have a chemistry lesson this morning, but they were using compounds like methylformate, ammonia, which I'm sure you're familiar with, sulfur dioxide, and methyl chloride. All of these are toxic, and many of these are also very flammable. And this really was a problem because if you had a leak of the refrigerant out of the refrigerator, it could harm you, it could harm pets, and it could also lead to a fire in your home. So in 1928, Thomas Midgley, he worked for General Motors, and he was a mechanical engineer, and he was also a chemist. So as Thad mentioned, I'm a chemical engineer. And I would say if you're a mechanical engineer and a chemist, then you're a chemical engineer too. And he was interested in refrigeration. And you can imagine why, right? You know, General Motors, if you wanted to keep cool inside your car, you rolled the window down. And I can still remember as a child riding in my parents' car and my grandparents' car, and it had a crank window, which I don't think you can find anymore. And when it got hot, you rolled the window down. And when it got cold, you rolled the window up. Well, Thomas Midgley was tasked with trying to figure out a better way of doing that. And could you build an air conditioning system for a car? And one of the things he started looking at was the refrigerants that were being used in these General Electric refrigerators. So ammonia, sulfur dioxide, methyl chloride. And he started looking at the elements, nitrogen, hydrogen, sulfur. And he looked at the periodic table and he said, all right, well, they're using carbon, nitrogen, oxygen, sulfur, chlorine. And he noticed this element was missing. And he wondered, I wonder why no one's using fluorine, and could fluorine be used to make new refrigerants? So he ultimately developed this refrigerant. It's called dichloro-difluoromethane. Here's its structure. So it's got one carbon atom, two fluorine atoms, and two chlorine atoms. And this was known as a chlorofluorocarbon because it's got chlorine, chloro, it's got fluorine, fluoro, and it's got a carbon, okay? And turns out that it was non-toxic, it was non-flammable, and it was very safe, and it had a boiling point that would work very well as a refrigerant. So this really became like a miracle fluid for replacing these refrigerants that were very toxic and flammable. Now we finally had a refrigerant that was non-toxic, non-flammable. And this is where the DuPont company came in. So remember, Thomas Midgley worked for General Motors. General Motors makes cars. They don't make chemicals. So General Motors came to DuPont and said, you know, we would like you to manufacture these refrigerants for us, and we will buy them and put them in all of our cars. So DuPont took a look at this in the 1930s, and they figured out how to manufacture at large scale this refrigerant. And they manufactured millions of pounds of this refrigerant for General Motors. And in addition, they looked at other refrigerants, and I won't go into a lot of details about the chemistry, but they have different boiling points. You can see that the one in refrigerators boils at -30. This one boils at close to room temperature, 24 centigrade, this one higher, this one lower. And they're used in a lot of different applications. They could be used for chillers, for large buildings, for cooling large buildings. They can be used for cleaning circuit boards that go into electronics. They can be used for cooling display cases in supermarkets. So a variety of different refrigerants are used for different purposes besides just what you might have in a refrigerator or in a car. So let me kind of come to 1968. So I was born 1966. In 1968, I'm sure you remember the Apollo missions. And Apollo 8 was a very famous moon mission. It was the first time that astronauts had left Earth's orbit and gone to the moon. They didn't land on the moon, but this was the very first time that humans had ever left Earth orbit to go and circle the moon. And so they left on December 21st. They got into the moon's orbit on December 24th. And as they were coming around the backside of the moon, and so this is the moon's surface, and as they come around the backside of the moon and they're looking out into space, this is what they see. They see the Earth. And they see it for the first time from space. And it really caught the astronauts by surprise because they noticed a few things. They noticed, one, just how beautiful the Earth is. And you can see the blue of the oceans. You can see the white of the clouds. But they also noticed the stark darkness around the Earth. There's nothing out there around us, right? We're all out here by ourselves. And so astronaut William Anders scrambled to try to find a camera inside the spacecraft so that he could take this picture. And this picture has a name. It's called Earthrise. And it's in honor of the Earth sort of rising over the surface of the moon. And it really, for the first time, it instilled in scientists this idea that we need to take care of the Earth. And that this picture is credited for beginning the environmental movement. And in the early 1970s is when you really started to see people paying attention to pollution. And a lot of that they attribute to this picture that Bill Anders took on that mission. So 1974, these three scientists, Paul Crutzen, Mario Molina, and Sherwood Rowland, they came up with a theory. And their theory was that these chlorofluorocarbon refrigerants, these miracle fluids, these refrigerants that are non-toxic, non-flammable, millions of pounds per year are being used. They're being put in refrigerators and air conditioners, in cars and trucks, in boats and airplanes and buildings. They're going everywhere, right? They're being used for all types of air conditioning and refrigeration. It's a huge, huge business for many, many companies. These three scientists say, we think that when these refrigerants escape and leak out of the system, they're so stable that they can make it all the way up through the Earth's troposphere, and they can get to the Earth's ozone layer. And when they do, in the Earth's ozone layer, there's this equilibrium between ozone. So ozone is O3, and UV light interacts with ozone to make oxygen and oxygen radicals. And these oxygen radicals and oxygen go back and make ozone. And so what happens in the ozone layer, which is around the Earth, is you have ozone going to oxygen and oxygen radicals and oxygen radicals and oxygen going back to ozone. And the ozone layer protects us because as these UV radiation from the sun comes towards the Earth, it interacts with the ozone, which prevents the UV radiation from striking the Earth, or prevents a significant portion of it from striking the Earth. So these scientists said, wait a minute, we think that these chlorofluorocarbons are now in our ozone layer and they prevent oxygen and oxygen radicals from going back to making ozone. So the ozone can still make oxygen and oxygen radicals, but it can't get replenished and make more ozone because of these chlorofluorocarbons. And this was their theory. Well, it kind of reminds me of today a little bit and climate change. Because what did people say? They said, nope, you're wrong. That's not right. Can't be true. You don't have any proof. The chlorofluorocarbons, the refrigerants are not depleting the Earth's ozone layer. This is a huge business for lots of different companies and countries. We're making millions and millions of dollars on the sale of these refrigerants. We need them. You're wrong. You're wrong. You're wrong. Well, that was 1970s. About 15 years later, in 1985, these three scientists, Joe Farman, Brian Gardner, and Jonathan Shanklin, now have the technology to make weather balloons. So these are very large balloons that they fill with helium, and they can attach scientific instruments to the end, and they can launch them from the Arctic and the Antarctic, and they can go up high enough in the Earth's atmosphere to where these instruments can sample the ozone layer, and they can sample whether there's chlorofluorocarbons. And what did they find? They found chlorofluorocarbons in the Earth's ozone layer, and they also found the ozone layer was decreasing in concentration. And this picture is referred to as an ozone hole, meaning that the concentration of ozone over, in this case, the Antarctic, is starting to decrease. And as the concentration of ozone decreases, remember that UV light from the sun can go through. And now the concentration of UV light hitting the surface is much, much greater and now can cause significant problems. So again, what do people say? What do people say? Well, no one lives in the Antarctic. Who cares? There's no plants there. There's very few animals, if any. It's really cold. No one lives there. Who cares? It's not a problem. Don't worry about it. Keep making chlorofluorocarbons. We make lots of money on those. Keep making them. So what do? They keep sampling the ozone layer. And they start to notice that this hole is getting bigger and bigger year after year after year. Well, eventually this hole gets large enough to now it's starting to touch countries where people do live. Like here, right? Here, this is Australia, right? Bottom of Africa, India, and this thing is getting bigger and bigger. So now it is touching places where UV light can hit humans, plants, animals. So finally, people start to pay attention. So in 1987, so this is the year I went to work for DuPont, 197 countries come together and sign what is called the Montreal Protocol. And it's hard to imagine 197 countries coming together and agreeing on anything, right? You think about the US and where we are today. But 197 countries came together and agreed that these chlorofluorocarbons, as useful as they are, we've got to do something. We've got to phase them out and replace them with something that's safer for our environment. So in the cars, like we were talking about earlier, and in the refrigerators, we were using these chlorofluorocarbon refrigerants. that were linked to the depletion of the ozone layer. So they had an ozone depletion potential, and we needed to improve that. And so the first thing I worked on were developing these what are called hydrochlorofluorocarbon refrigerants. And what we did was we took the molecule and we started replacing the chlorine with hydrogen. And the hydrogen was safe for the ozone layer, the chlorine was not. And ultimately, we developed these refrigerants called hydrofluorocarbon refrigerants. So these hydrofluorocarbon refrigerants don't have any chlorine in the molecule. It's only carbon, fluorine, and hydrogen. And they have zero ozone depletion potential. So they're safe for the Earth's ozone layer. And they also worked quite well. They had a boiling point that was close to what we were trying to replace. And so most of you probably have this refrigerant in your refrigerator in your house. You have this probably in your car. And this is what's been used now for about the last 25 years, is hydrofluorocarbons. Well, let's go back to the ozone story. This is a plot of the ozone concentration in the Antarctic. And in 1960, it was about 300 parts per million. And you can see how rapidly the ozone concentration over the Antarctic was decreasing. We started producing these new hydrofluorocarbons in the early 1990s. And that's when we started to really phase down the use of the chlorofluorocarbons. And you can see that this sort of started to stop the decrease of the ozone concentration. Instead of this continuing to go down, it started to level off and flatten out. And now let's go to 2020, and we can start to see now that the ozone concentrations over the Antarctic are slowly starting to increase again. And so this part of it is all models as to what we predict. And we think that by 2100, the ozone concentration over the Antarctic and other parts, the Arctic, will be back to about where it was in the 1960s. So, a couple things to take from this graph. Look how long it takes for the Earth's ozone layer to recover. Probably take about 100 years for it to fully recover. Environmental change takes a long time. It's on a long time scale. And it also shows that even though we created this problem, we can also solve this problem. When everybody works together, especially various different countries come together and agree, you can make a change that affects the entire planet. And so that's, I think, one statement that I'd like for you to hopefully remember out of my talk today is that global challenges can be solved, but it really takes everybody in all countries coming together and agreeing to work on it together. So now let's fast forward to today. So 2016, this is when I joined KU. In October of 2016, 170 countries come together and they sign an agreement called the Kaligi Agreement. And this has to do with the global warming potential for hydrofluorocarbons. So even though we solved this ozone depletion potential problem, now people are concerned about the global warming potential for hydrofluorocarbons. So now we have these countries coming together and discussing how are we going to phase down the hydrofluorocarbons that I worked on inventing to something that's going to be safer, not only for the ozone layer, but also for reducing global warming. And now you kind of go back to those original scientists who said, you know, I think refrigerants might be depleting the ozone layer. And people saying, no, it's not happening. Well, where are we today? Oh, the Earth's not warming up. It's just the natural cycles of the sun. CO2 is not contributing to global warming. Climate change isn't real. Climate change is fake news. Uh, that's where we are, right? And and so it's going to take all of us to come together to figure out how to solve some of these global challenges related to climate change and the earth warming. So I thought I'd show you a few pictures here at the end. This might be what you see outside your house. This is your air conditioner. This has a refrigerant in it called R410A. When you go to the supermarket, maybe Dillon's, you see these supermarket display cases. This has a refrigerant in it called R404A. Both of these refrigerants I invented. So when I go to the supermarket, I look inside the display case. I don't necessarily look at the food. I look for a little tag up here in the top and see if it's got R404A in it, because I know that was something I invented 25 years ago. Well, what does it look like behind the scenes? So inside your air conditioner, you have about 5 to 10 kilograms of refrigerant. Inside a supermarket, you might have 1,000 to 2,500 kilograms of refrigerant. And then you think about how many air conditioners, how many supermarkets, how many trucks, buildings, and you start adding up the amount of refrigerant. And it is literally billions of pounds of refrigerant all around the world that are being used for cooling and refrigeration. And we've got to figure out now how to phase those out and create new substitutes that, again, are safe for the ozone layer, but even more importantly, if they leak, they don't contribute to global warming. And so that's where we've been fortunate to get some federal funding. So I've gotten 3 awards from the National Science Foundation that total about $2.5 million. Where KU is the lead university, working with other universities like Notre Dame, Rutgers, Texas A&M. We're working with national labs like Brookhaven and Oak Ridge and NIST. And we're working with companies to try to develop these alternative refrigerants. And I just thought I'd go back and show you again some of the students that are working on this with me. So as I mentioned, Kaylin went to the University of New Mexico. She's getting her PhD. She already has a master's degree and an MBA, and she's interested in starting her own company one day. As I mentioned, Abby went to Bethel College here in Kansas. Her undergraduate degrees are in chemistry and mathematics, and she's working on getting her PhD in chemical engineering. Andrew went to Baylor University in Texas, and he's working on getting his PhD. Ethan went to KU as an undergrad and is now working on his master's degree. And Kareem went to University of South Florida, and now he's working on his PhD. So all 5 of these students are working on this project with me. And we call it Project Earth, and it stands for Environmentally Applied Research Towards Hydrofluorocarbons. So Project Earth. Not going to spend too much time here, but each university has different areas that they're focused on. We're doing a lot of measurements and modeling. Notre Dame is doing molecular simulations, trying to use computers to calculate some of the properties for us. The folks at Texas A&M are working on making some of the materials, and Rutgers is doing some of the spectroscopy, as well as Texas A&M is doing some of the modeling. And so I thought I'd just give you one example. So the air conditioner for your house, it has this refrigerant, R410A, and it's actually a mixture of 2 refrigerants. It's 50% of this molecule and 50% of this one. And this one actually has a fairly low global warming potential, and this one has a very high global warming potential. And so rather than remove this refrigerant and have to dispose of it, usually through incineration, what we're working on is how to separate the one that's got a low global warming potential and how we can reuse it while the one that has the high global warming potential, we want to figure out how to use chemistry to make that molecule into something that's safer. And so that's kind of what's shown here with the arrows, is that this one can be recycled and reused as a refrigerant, maybe in a mixture with other refrigerants. And this one that has a high global warming potential, we'll do chemistry to make that into something that has a much more environmentally friendly footprint. And the students are looking at 3 different approaches to do this. Kaylin is using a material called an ionic liquid. So these are sort of like salt. So your table salt melts at about 800 centigrade or 1600 Fahrenheit. These salts are liquid at room temperature. And so what she's doing is looking at these salts and figuring out ways that one refrigerant will dissolve in the salt and the other refrigerant will not. And in that way, we can separate those refrigerant mixtures. This is a publication that they just recently got. So we also work very hard with all the students to publish their work. I think we've had probably about 30 publications since I arrived here at KU. Andrew is using what's called a porous material. So these are materials that are called zeolites. And here the pores can be designed such that one refrigerant can get into the pores and the other one cannot. And we can use that as a way of separating the refrigerant mixtures and using the ones that have good environmental properties, and then the other ones we'll figure out how to convert into other products. And then Abby is working on membranes. So the same sort of thing where she's going to use a membrane to separate the gases and be able to reuse the gas that has the low global warming potential. So maybe just to summarize what Project Earth is about is we'll provide the refrigerant industry with a technology for recycling refrigerants. And we believe this is valued at more than $1 billion. It'll really revolutionize the refrigerants industry and provide a process for a lot of EPA certified recyclers. And we've had the 2 largest refrigerant recyclers in the United States contact us and are interested in working with us. And we also recently had the world's largest refrigerant recycler globally contact us and is also ready to work with us. And to give you an idea of the impact that this project could have is by recycling these refrigerants and developing materials that have lower global warming potential, it would be equivalent to reducing CO2 emissions by 175 million metric tons a year. And that would be equivalent to like taking 50 million cars off the road. So, I mean, it has a tremendous impact that it could make by being able to recycle these refrigerants. So I thought I would just close in the last couple minutes with a couple other grand challenges that we face. And this list was actually put together by Richard Smalley. So he was a Nobel Prize winner from Rice University. And this was his top 10. And, you know, sustainable energy, clean water, available food, here's climate change, poverty, terrorism. At the time he put this list together, infectious disease was number 7. We might argue that this one is now closer to the top. Increasing population growth, democracy, and education. This was his top 10 challenges that were facing the world. And I thought I'd show you this chart because I thought this was pretty interesting. So I was born in 1966. So in 1966, there were about 3.5 billion people in the world. And now fast forward to 2021. And, you know, we're approaching like 7.8 billion people, 7.7 billion people. So in roughly half of my lifetime, because I'm 54. So we doubled the population of the Earth in half of my lifetime. And you think about how long it took us to get to 3.5 billion people, right? Thousands and thousands and thousands of years to get to 3.5 billion people. And in 50 years, we got more than another 3.5 billion people to get up to 7.7 billion. So you can see how population growth has really contributed to some of these challenges that we're facing. And this one is interesting. So the United Nations estimates that in 2030, we'll be at about 8.3 billion people. And the food demand will increase by 35%. The water demand will increase by 40%. And the energy demand will increase by 50%. So then you ask, well, where is that all going to come from? Right? Can we continue to keep increasing the population? And will there be enough food, clean water, energy for everyone's needs? So in summary, I'd like to just go back and reflect on, global challenges can be solved. And I was really, it was an honor for me to get to work on refrigerants and invent hydrofluorocarbons and replace the chlorofluorocarbons that were linked to the depletion of the Earth's ozone layer. And it showed that it could be done, right? And we did it. And we really have shown that the Earth's ozone layer is healing. And now, the big challenge in front of us is climate change and what can be done in order to slow that down. And I do think that sustainability is the key challenge facing humanity. How do we continue to live on this planet and do it in a sustainable way? And so I thought I'd just finish with this picture. It's where we all live. We live on the Earth. And if you look out here into space, there's no other place for us to go. Maybe there'll be a few people on the moon again one day. Maybe there'll be a few people on Mars one day. But for those 7.7 billion people, this is where we all live. And we've got to take care of it because we don't have anywhere else to go. So with that, I'll be happy to answer any questions. I really appreciate you joining this morning. Yeah.
Mark, before you go to the chat and you can see some questions and comments there, I'm reminded of Friedrich Buchner's idea of vocation, which you have. You not only have a career, but you have a vocation. He said about folks that their deep joys or gifts meet the earth's deep hurts is a vocation, a calling. And you've got to get up excited every morning because you're dealing with something so important. And besides that, don't say my grandparents. I remember my parents having an icebox. Good Lord, that shows my age, I guess. But anyway, this is just wonderful. So if you want to, would you go to the chat line and just see the questions that are there? You've got a couple of them and some comments too.
Yeah, I'm just looking back to see which is the first one. Would it be possible to get a copy of your slides? Absolutely. I don't know if it's easier for me to just send them to Thad, or is that the best thing to do, Thad? Or
yeah, I will send them out to people that want it. Yeah.
Okay. I'll send a copy to you, Thad, this morning, and then feel free to send it to anybody who would like them.
Okay.
When and how were the first home air conditioners made and used? That's a good question. So about the same time that that Thomas Midgley was working on air conditioners for General Motors, Willis Carrier, I think, who started the Carrier air conditioning company, was interested in home air conditioners. And so those were probably also in about the same time frame. The very first ones were probably just window units. because I can remember when I was a child, we had one window unit for our house. And when it was in really hot summertime, we'd all stay in the same room together because the bedrooms were too hot to sleep in. And then eventually central air conditioning and other technologies came along, and then you could cool your whole home. But that was probably again like around the 1940s when Willis Carrier was experimenting with air conditioners for homes. Effective air conditioning will be a critical part of climate change mitigation. Will these refrigerants be inexpensive enough to put in wide use in low and middle income countries? That's a great question. It turns out that these new refrigerants are actually more complex. They're more difficult to manufacture, and they're more expensive. So, I think that's a challenge in front of us, is to figure out how to continue to make new refrigerants that are less expensive, but yet environmentally friendly, such that they can be used by all incomes and all countries. So that, I think that's a great question, and it's still an active challenge that I think still has to be figured out and met. Project Drawdown lists refrigeration as the #1 solution to reversing climate change. Elaborate how and how soon? Yeah, so this is a good question too. I was just looking at this last night. So when you look at the contribution to climate change from refrigerants, it's about 8% of the total contribution to climate change. 8% comes from refrigerants. And of that 8%, about 5% of that comes from the energy that's used to run the equipment. And the other 3% is the contribution to the gases leaking out of the systems. So then you ask yourself, okay, well, if refrigerants are only 8% of the contribution to climate change, where's the rest of it? And the rest of it, or the bulk of it, I'd say probably 90% of it, is from CO2 emissions, right? CO2 emissions are the major contribution to climate change. And what makes that a challenge is that that's a difficult problem to deal with. And I've worked on it even at DuPont. It's going to take time, and we've got to start on it seriously now, because if we want to, let's say, electrify our transportation system so that we can remove 200 million tailpipes from the country, that's going to take time. And even if you electrify transportation, how is the electricity made? Is it going to be made with solar? Maybe some. Is it going to be made with wind? Some. Is it going to be made with tidal power? Some. Could it still be made with nuclear? Some. So you've got to have sources of electricity that are green, and you've got to bring on these electric vehicles. And there's major challenges right now with electric vehicles. The biggest one is charging, right? Nobody wants to have to spend hours and hours charging the batteries, and you're limited on how far you can go, right? You might only be able to travel 300 miles on a charge. So we need batteries that can hold much larger charges, and we need batteries that can be charged in minutes, not in hours. So, we're going to move in that direction, but it's going to take time. And my guess is it's going to take us another 100 years to fully electrify the transportation area. This is one of the best presentations I've heard. Thank you very much. Describing the history of refrigerants, their impact on the ozone layer, what the future holds for research in this area. Thank you. So thanks for that nice compliment. Again, I bring it back to the students, right? Like I'll be 55 on my birthday, and they're all early 20s. I'm trying to instill in them this passion for inventing, for creating new things, for trying to solve really, difficult problems, and showing them that it's possible, and giving them the tools that they need in order to accomplish these goals. I mean, some things maybe that people don't realize about being a professor. They think, oh, you go teach your class and, but I probably spend 70% of my time writing research proposals to get funding from federal agencies, from companies, because just to run my labs and support those 10 graduate students, it costs me about $1 million a year. So it's like I'm running $1 million business where I have to make sure that I get the $1 million from various different sources in order for those students to be able to still come do their work, graduate, another set come do their work, graduate. So it's a little bit of a challenge to run a research laboratory in a big university and keep it funded. A group within Rotary is looking to expand solar-powered community refrigeration to reduce food waste and provide cold chain for vaccines. How does your work support expansion of distributed solar refrigeration? That's a really good question. So there are some refrigeration technologies that can directly couple to solar. And so we are looking at that, and we're looking at what refrigerants might work the best in those applications so that they're the most energy efficient. I think a lot of it comes back oftentimes to energy efficiency. If you're going to develop a new technology, whether it's with a refrigerant or other, you want it to be more energy efficient than what we have today. Otherwise, you're actually maybe doing more harm than good. So it always comes back to energy efficiency. If you can develop technologies that are more energy efficient, then you've got something that's a winner. And also the cost, right? The capital cost of that technology has to be something that's within reach compared to what people are using today. Dr. Sherry Rowland, one of the 3 scientists that won the Nobel Prize for showing refrigerants were depleting the ozone layer, was a professor of chemistry at KU before moving to California. Yeah, thanks for mentioning that. I was told that. So yeah, there's a nice connection there between Dr. Rowland and the University of Kansas. What chemical were in gas refrigerators? So I'm trying to remember what gas refrigerators means. I know, like, if you're referring to, like, if you had a refrigerator like in your camper, so like mobile homes and campers, those refrigerators actually are powered most of the time by propane. So maybe that's what we're talking about here as a gas refrigerator. So if your refrigerator is not running on electricity, but it's running on like propane or some gas that you're burning, right? And you're like, how does that work? That actually is an absorption cooling refrigerator. So rather than having a compressor that runs on electricity that has a motor that compresses the gas, that's a vapor compression system. These refrigerators use absorption technology, and there the refrigerant is absorbed. Like, let's say the refrigerant is ammonia. and it's absorbed into water. And now you've got this ammonia water solution. You use a flame that's from propane, and the flame heats up that solution of ammonia and water, and the ammonia comes out of the water. And when the ammonia comes out of the water, it can recycle back through the refrigerator for cooling, and then it goes back into the water again. And then it heats it up, drives the ammonia out of the water, and then through the refrigerator and back into the water again. And so actually you're using a flame, you're using heat to run the refrigerator rather than electricity. And actually that concept was originally developed by Thomas Edison. And Einstein actually worked on this too. But it turns out for small systems, it works okay. But for large scale systems, it's not as energy efficient. And that's why you don't see it more other than like in mobile homes, campers, and applications like that. What about extracting the chemicals needed for battery storage? So actually I am working on that. So not everything I do is refrigerants. So I have a student, his picture was in that one back a few slides ago. He's actually from India, and he's working on how to recycle lithium-ion batteries. And we actually have a company that contacted us recently and is interested in pursuing this with us. And so in lithium-ion batteries, the cathode, so you have an anode and a cathode. The anode is usually made of carbon, and the cathode is made of what are called critical metals. So these are metals that are not very abundant, and we need to be able to recycle them. And so some of those metals are lithium, cobalt, particularly cobalt, because it comes from certain places in the world like the Congo, where the labor practices are pretty poor. And so what we're doing is trying to figure out how to recycle the lithium and the cobalt from lithium-ion batteries so that those can be reused to make new lithium-ion batteries. And I think this is going to become more and more important, because as we go further and further into electrification of the transportation system, the size and scale and number of batteries that will be used in these cars and trucks are going to rapidly increase. And we're going to need to be able to recycle those batteries effectively. You know, in your car today, you have basically a lead acid battery. And like 95% of all lead acid batteries get recycled. So there's a beautiful recycle of lead acid batteries today. That doesn't exist for lithium-ion batteries today. And so that's one of the reasons that we're working on that. Why is it so cold in outer space? It's another good question. If you're much farther from the sun than we are, like, you know, we're kind of at the perfect spot in our solar system from the sun. And it makes the Earth just the right temperature. And if you go even to the moon, the temperatures on the moon from night and day can vary from like plus 200 Fahrenheit to minus 200 Fahrenheit. So if you go to the next planet away from us, Mars, the average temperatures during the day are below 0 Fahrenheit. So you've got to be just the right distance from your star, right? Our star, we happen to call the sun, but you got to be just the right distance. And when you look at space in the universe in general, most things are not close enough to their stars to be just the right temperature. The other extreme is true too. Like if you go to Venus, there it's way too hot to have anything survive. And in fact, there's only been a few probes ever sent to Venus, and they don't last very long. Like once they go through the atmosphere, they basically just dissolve because the atmosphere is acidic. It's very high temperature. That's why you don't have any rovers on the surface of Venus. So yeah, you got to be in just the right spot. And luckily for us, the Earth is in just the right location so that the temperatures are just right for humans. I think that's the last question, Thad.
I think so. And I've had some private messages. They may be contacting you, and then you have your information there on that last slide. We've come to the end of our time. I really want to thank you, Mark, again, not only for what you've done, but what you're doing with us in terms of educating. And I think I've certainly learned a lot. So again, thank you. And let me know, folks, if you need something, well, just contact me and we'll send a recording out as well. So thank you much and see you next week, I hope. So,
Okay. Bye, everybody.